话筒会正确放置。
Hello.
以上锁，已解锁，请取出话筒。
Hello, testing.
以上锁。
Heng, are you not here on Monday? What happened? Huh? Oh, no, not today. Okay, the thing is, we have a pop quiz now, between now and then. So if you disappear, then you might miss the quiz. So it's about like 5%. Yeah, we got 10 weeks at having pop quiz. For those we don't have assignment. Yeah, so you need to maybe inform me on what. If you want to see your quizzes, you can come and see and take a picture. If not, I'll just keep it for record. Yeah, if you want, you can come and have a look. Yeah. Let's see. Okay, so unfortunately, the handheld one is out of battery, so maybe I need to use the static one. But today I bring some notes here that we discussed on Monday. Okay. So the first one we saw on Monday was the hopping. Okay, so this is the simplest way. The simplest way is to hop. So the hop link is the simplest way to link two circles together. This one, not this one. Okay. So why I make this one up? So if I put it around, right? So here is a little bit different. So if you can see from far, right, there's some twist happening here. Okay. So if I pull this twist, right, go to here as well. So what you can see here was like there are two loops. Okay. So last time we say that this yellow loop here is a generator of all the other loops. Can see? Okay, so the point he hold here is like the base point x naught. Can see the pink loop here? Can you see? Okay, there's no way to remove this two loop here without breaking the original circle. Can see everyone? Okay, so this is like this yellow circle is an infinite generator of the fundamental of the complement of this blue circle. Okay. Why is it complement? Later we'll learn something called right. We need homotopy, right? So basically, all the loops that loops around this circle is homotopy. This. Right. Other thing. So this one, borrowing ring here. So we have this borrowing ring here. I think it's also the simplest one to join three circles. Okay, so basically you cannot remove any circle without breaking it or untie it. Right. Okay. So later I'll pass around. You can make it into the configuration that we discussed yesterday. Okay, but let's say we twist one of these crossing just now. Then we can actually remove the third one. Okay, well remove. Oh, so actually you can pull this third out. Okay, I'll pass this ring for you to play around. Okay. If you like, you can destroy them because I can always put them back. I mean, you can pair with them. Okay, maybe I start from there. Or maybe one each time. Yeah. You can pass around. Yeah. Another thing is I still want to advertise the revision assignment. So finally, our algebraic geometry notes is up now. Okay, so I put the notes on my website already. So thanks for those who are helping, including the masters. Hey, the masters, are you guys attending this course regularly? Oh, I know you are not enrolled here, but just want to ask, what's your commitment? Uh, depend, not because I want to give some job to you guys. Okay, never mind. Let's see how it goes. Okay, so actually there are very two lovely cover here, actually made by Lydia. They're very good. You see, my website become more beautiful. I'm tempted to ask Lydia, can you help me do a general topology one? Okay, you can think about it. If you got time, you can tell me. Then we will have a third picture. Sure, sure. Okay, sure. Yeah, I think it's pretty good. And then seems like there's some continuation here. Okay, it's like, you see, this one is the third viewpoint here. And then this one is the first person viewpoint here. Okay, there's some, yeah, kind of there's some story. Okay, if you can, then let me know. 什么？哎，坏掉了。哎，please sponsor one iPad. Okay. Okay, sure. Okay. Another thing is, yeah, there's something I want to show you. Something written by Adrian, maybe. Hopefully, can motivate you to do the revision assignment. Okay, so I want to share one of the part. Where is it? Okay, here, maybe start from here. So, among the courses I've undertaken, this has been undoubtedly been one of the most demanding. They come to a point when, overwhelmed by its depth, I set it aside, entirely convinced that the subject was too vast and the obstacles insurmountable. My thoughts fell entangled in invisible threads, knots of confusion, weaving endlessly and obscuring the light vision. Okay, this is the part I thought is coming from ChatGPT. Because so many big words here. Okay, anyway, but you get the point, right? Again, continue. Yet clarity often emerges gradually in unexpected moment. As I resumed the study on my own, yet again assisted by me, with the typesetting of his lecture notes. So he did it after the SEM. After the SEM. Again, most of the work actually done after the SEM. The material began to unfold with greater coherence. Okay, what had once seemed opaque revealed itself as intricate yet profoundly structured. And algebraic geometry, initially a source of despair, transformed into a subject of elegance and depth. Okay, through this process, I came to realize that this discipline demands not only technical mastery, but also a reorientation of perspective, a willingness to see differently. So this course is almost the same difficulty. Okay, so that's why I urge you, okay, this time actually I force you to type this lecture note because I want to see how you do revision. Okay, I want to see how you do revision. Because he's not just typing for the sake of typing. When he type, he will come and ask me one, hey, this part got problem or not? Or this part how to fill in? Okay, then you will see that what I'm trying to tell you or teach you. Okay, so you see this part here with greater coherence. Okay, I will always make sure that my theorem, my definition are actually connected one. Will be used next, will be keep using. Okay, so all of them are connected. Okay, this is my commitment to my note. Okay, and then yeah, last sentence here. Actually, this sentence is true for every pure maths course. Actually, the thing that we discuss could be the thing you have seen before. It's a different way we introduce it, or we use it, or we understand it. Okay, you must be able to achieve this. Okay, then this is then this will improve your understanding through the course. Okay or not? Okay. Okay. So if you are okay, actually I already arranged a schedule here. If you look back your course information. So oh yeah, this morning I have this calculus one class. I asked them, do you guys love mathematics? What do you think? There are 57 of them. Okay, not all of them are there, but I mean, only maybe 4 of them raise out their hand. So I'm like, shit. I cannot talk too much anymore. But it's okay. I think for now, at least their participation is still active. They ask question, answer question. I think should be fine. Hey, why the Moodle lag again? Since yesterday, this one, like this. Okay, never mind. I open from my drive. Okay, I need everyone cooperation here. So once we set this schedule, right? You like it or not, please type it out. Okay, you like it or not, please type it out. Mine is a second problem, but you have to type it out so that everyone can benefit. Also including you. Yeah. Okay, so I put out a schedule here. Okay, so first week we already assigned our class rep to do it, right? Our beloved Eric, right? So he's trying to do it now. And then I will try to ask him to set a standard or sample so that you can follow what we want you to do. Then the next week will be Larry. So Larry need to take note, prepare to type next week. Okay, and then follow up will be Hang Wei, Jing Shen. Hey, where's Ivan? Not back yet. Still celebrating. Hey, you not, oh, okay. Yeah, 问一下他哈，我要问他。Okay, Ivan, Hang, okay. And then this week I put a break here. One is we don't have enough people. Second is this week we might have a test. Okay, so I decided to break here. Yeah. What do you mean? Sure. No. So this class is a replacement class. Okay, so that you have one holiday within your semester. So that class will be used to do replacement class. Sorry, yeah, replacement class, and then we will use the replacement class as a test. But yeah, definitely. Okay, yeah. I think we need to decide this test soon. Maybe next week. Next week I will ask you again. And then next we will continue with Lydia, Rachel, Xiaoyue, Haotian, Adrian, and then Eric again. So I put over the 2304 first. Okay, because I think they need to submit FYP soon. So I will make them do first. And then for the rest, do it later. And then we got a week 14 also. Okay, so these are the 2 blank that I hope some of the master can fill in. Okay. Yeah, if cannot, then I will just let them fill. If can, then I also want to get some input from you guys. Depends. If you can, you let me know. If cannot, never mind. Okay, everyone okay? Clear? Yes. Hey, why are you not on the list? How come? Hey, wait, let me count. 1, 2, 3, 4, 5, 6. Oh, we got 12 now. Okay, in that case, then I remove this Yao Yichen, no? Then I put you in. Okay, you put to the last one. And then Eric, see how? Maybe can fit. You can fill the gap. Okay, sure. I'll let you fill the gap then. Okay, then good. Then that's good. Okay, so for this revision, right, I think we achieved one consensus is within a week you should type out the draft, which is my version. Okay, so if you look at my uploaded notes, right? Have you looked at my uploaded notes? Okay, this time I add some notation here. I got this cross, this Y. All of it you need to fill in. The first draft maybe you don't need to fill in first, but the second draft you need to fill in, which is the following week. Okay, so for example, this right, easy. Okay, for the first draft you also type easy, but you will have to add in a solution link and then prove it. Okay, the two direction. Okay, and then I asked Yao Yichen to make a sample so that you know what is happening. Okay, make sense, huh? Okay, so for all the easy, obvious, the thing that we claim should be fill it in as a solution, but not fill it as a first read test. Okay, because we don't want this argument to obstruct our first reading. Okay, make sense? Okay, yeah, hopefully Eric can put out the guideline in this week. Okay, for this picture, right, there are a few ways to deal with it because sometimes picture could take a lot of times. So I allowed you to submit a screenshot version. Okay, if we want to make it a drawn version, we could make it ourselves. But if you have time, you can draw it. For example, you can ask Zheng Ye also. Zheng Ye now is professional in drawing now. Algebraic, no, general topology is drawn by him. Yeah, maybe you can ask him. Also, these notes, right? Actually, there's a package called Break. I think is Adrian learning it? Yeah. So once you learn, maybe you can share it on Moodle, and people can try and learn together. Okay, but picture is not the main focus here. The main focus for this revision assignment is all the argument. Okay, all the proof, all the definition, whether correct or not. Okay, make sense? Okay. All right. I think that's it for the update. Any question from you? Any question from you? No question. So Zheng, you want to take this course or not? Okay. What's the course you're doing now? Okay. 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 Yeah. So you can really just choose one. 赵生，赵生 people calling you. How about 赵生? What are you doing now? Huh? ALA 啊？哎呀，drop ALA 了。哎，waste of time. Okay. Okay. Okay, let's resume our proposition that we left on Monday. So use this now.
正在连接。开始连接话筒，已解锁，请启动话筒。
All right, so let X be a topological space. So yesterday we claimed that the set pi1 x x naught of all homotopy plus of loops and the best point S naught is actually a group. And what's the name of this group? Anyone know? Fundamental group. Okay, this is called the Okay, fundamental group of X. The line broke. Wait, let me rejoin. Okay, call the fundamental group. What's the product structure? Anyone remember what's the product structure there? What's the product structure? Yeah, so what's the word? This is what we call a concatenation. Okay, we concatenate again two paths together. So we can do concatenation here in particular because the first path end at the place where the second path start, so that we can concatenate. If they start once end at a different place and they start at a different place, then they cannot get concatenate. And so you cannot continue. Hey, why? Yeah? Is there any problem with your Wi-Fi or not? Cannot call back. Go through this proof a little bit careful. So this is the first kind of algebraic topology proof. You should really learn it. All right. So wait. Okay. So first, we prove that product of homotopy classes of path is well defined. Okay. So what do you need to take? Want to show that if alpha prime. So this I here, I think we didn't introduce this notation yesterday. This is the unit interval. And let's take another two representative such that all their connecting point is the same. Okay, so where they concatenate such that alpha is homotopic to alpha prime and beta is homotopic to beta prime. Then I want to show that the first product is homotopic to the second. Okay. All right. So what do you think? Okay, so the picture, you should have picture in this class, right? Always. So we got, let's say, an alpha. Oh, there's some subtlety here I want you to notice. Oh, I didn't write down the product, huh? So let me write down the product here. Just now, Eric mentioned, huh? Sorry? Yes, all these paths are loops, by the way. We are just talking about loop space, not random path space. So with alpha times beta equals to alpha star beta, where what is alpha star beta here? So alpha star beta here is really speeding out. Okay, speeding out the alpha first, okay, and then speed out beta. Okay, yesterday we discussed about this 2x minus 1, right? Okay, to make sure you start at the right place and end at the right place. Okay, so we define what the path concatenation is, and then we define the product as an equivalent constant. So here, so we take alpha here, okay, and then we connect with beta, let's say like this. Okay, so you see, a bit different from a function composition. Do you remember or not? F, Gx, you do F first or Gx first? GX, no? But here, we do alpha first. So please take note of this difference. We do alpha first. So because it really matches up with the way we draw our. Yeah, sure. We talk about the loops. Sure. Okay. Can you, in your mind, imagine these two is the same? Because I think in this presentation is more general. Okay, so this is a more general argument here. Okay, let me put here. This is a more general. But in your mind, for our case, alpha 0, alpha 1, or beta 0, or beta 1 is the same. Okay, but what I want to draw here is more general. Okay. Oh, no wonder Adrian asked me whether our case is loop apart. Okay, so let's say our alpha is homotopic to another alpha prime. Okay, so maybe we draw like this, alpha prime, right? So there's a homotopy between them. So yesterday we realized that homotopy is like this, right? Or a family of path, right? Family of path with the endpoint the same. Okay, and then beta prime is another path that's homotopic. Okay, so the question now is, if I look at alpha beta as a whole path and alpha prime beta prime as a whole path, any homotopy between them or not? Any homotopy between them? You just compose the homotopy together. So you also speed up the first part of your homotopy and then second part of the homotopy. Okay, makes sense? Okay, so you try and write down the homotopy, but this is what happened. You also concatenate, right? In each level here, you also concatenate. Make sense? Okay, but to do that, you need to write down your homotopy first. So you need to give your homotopy a name. You want me to show you? Okay. Okay, let me show you once. So let's say we call the first homotopy, we say it alpha, gamma alpha, and then second one is gamma beta. Okay. So remember how many variable we take for homotopy? 2, right? Okay. So there's a time variable, there's a curve version, right? Okay. Gamma alpha xt, gamma beta st. Okay. So what's the composed homotopy? Okay, so I think so. Wait, let me think. So I think it should be gamma alpha x comma 2t star with gamma alpha x 2t minus 1. Okay, yeah, for every t. Okay, for every t, if you fix a t, so if you fix a time t, what happened here? You are picking up, okay, you are picking up one of the path from the family of path of homotopy alpha, and then second you pick up another one, homotopy of beta. So, 哪里写错? Beta. Yeah, thank you. Okay, makes sense. Okay, and then try and check. It is continuous, right? Because it's just composition actually. 什么? Oh, right. You are right. So how about how should I draw this? I think I just okay, wait. So maybe I just write like this. I mean, put a star here. Yeah. Okay. But I really want you to write down the explicit form. Try and write down this explicit form here. Okay. Yeah. Try and write this part down. Okay. Note that you see this is only 0 to 1, right? But this homotopy here includes the time variables or family of them. So you fix one time, you are just picking up one path, okay, and then you can go back to the definition that we have. Oh, then in this case here, I think I put the definition wrong, I guess. So by this definition, what we should get is, let me try. So if I fix a time t, so x will go to gamma alpha 2x t first, okay, and then we do gamma beta 2x minus 1 and then t. Okay, so we speed up this middle path here, okay? But the time is still the same. Okay, repeat the same time. Does it make sense? Okay or not? Should I draw it a little bit clearer? So for example, let's say this part here is gamma or gamma alpha, let's say s of 0.2, and then we join with the gamma beta as 0.2 also. Okay, and then because our homotopy need to live inside 0 to 1, so we speed up this part and this part. Okay, makes sense? Okay, so these are the things that I suggest you to write down when you do revision. Any question or not? Any question? Okay, another thing I want to point out is, make sure your order, okay, it's not like a function. We saw the composition is like left to right here. Function is right to left, right? So this one is left to right. Because why? Because you need to have this kind of image in your mind. Okay, I draw from here, draw from left to right. Why I draw from left to right and not right to left? Actually, this is a very good convention, you know. I mean, in Chinese old writing, right, you read from right to left. But nowadays, all the writing is left to right. English left to right. Chinese also, maybe Chinese, some of them is like up to down and then right to left. Okay, so yeah, there's some convention problem here. Sorry? Okay. Yeah. Okay, but the convention we pick here is from the left to right. Okay. So same as the reading. Okay. You read from left to right. Okay. Second, how about check the associativity? The associativity. Okay. So I simplified it. All the condition, I think we should know what happens. So to simplify it, we should get this. Let's have alpha, beta, and gamma together. So I would say that this course is almost like a restart of AA1. Almost follow the flow what we did for group theory. Prove something is a group, and then there will be a group action or something like that. Okay. But now you will see it in a different form, which is this fundamental group, a specific group. Okay. So what we're gonna do here, okay? What's the difference here? So let me write down what is going to happen. On one side, okay, on one side, how much you speed up actually? How many times you speed up? Can you see? Because you got two composition, right? So first composition, you already speed up once. Second composition, you speed up again. Okay, so 2 times 2 is a factor of 4. Okay, so you could imagine that if you do it step by step, alpha will get speed up by 4x. Okay, and then I mean for the left hand side composition, and then for the beta, it will be 4x minus 1. Okay, for the last one, you get gamma 2x minus 1. Okay, if you write down step by step, okay, meaning you do alpha beta first and then you do alpha beta. Alpha beta is the one part and then you do gamma. Okay, so you can see that these two get speed up from 0 to 1/4. And how about the other side? What do you think? How about the other side? How about the other side? The other side, you split out the last two first, right? Okay, so the last two will become taking point from half to 3/3, and then one of them is 3/3 to 1. Okay, and then the first one is from 0 to half. Okay, so become half bar 2x, and then beta 2 times 2x minus 1. I purposely write 2 times 2x minus 1 so that you can check where the 4x minus 2 come from. And then the last one is 4x minus 3. Okay. So the question is, can you produce a homotopy between these three parts or not? Okay, can you produce homotopy between these three parts here? Okay, so maybe you can graph it out actually. Yeah, we can graph it out actually. How about draw it larger? Okay, on one side is 0 to half, and then 3, 4, and then 1, and then the other side is 1, 4, and then 1. Okay, what is gonna happen here is from 0 to half here, right? It should be equivalent to the other side from 0 to 1/4. And then similarly, this 3/4 and 1/2 have to be the same point. And then similarly, you have to fix that one. Okay, so what's the homotopy you can present here? Okay. One way is to write down the explicit homotopy. But what we're going to do here is we just want to produce a parametrization. Okay, let's say, do you know how to go from this 2x parametrization to 4x? Let's talk about parametrization, reparametrization first, not homotopy. Okay. Reparametrization. Do you know how to reparametrize 2x to 4x? You need to multiply by 2. Okay, so the reparametrization here is 2x here. Okay, 2 times 2x. So I put an x here. So this x will represent the 2s. Reparametrization. You guys not familiar with reparametrization. So for example, alpha t become alpha 2t like that. It's a reparametrization. So let's say okay, alpha t equals to 2t. Then alpha 2t will becomes alpha become 4t, right? Okay. But if you restrict, for example, I think this is something that we didn't really focus much on when we teach lower form max. So for example, let's say we restrict our t between 0 and 1 here. Okay, for the first one. After parametrization, right, we can get the same curve, but you need to adjust your domain a bit. Okay, so how to adjust your domain? I think you go from 0 to half, you already get everything. It's the same curve. You understand or not? So we speed up, then we reduce domain. It's the same curve. Try and plot it out. It's the same curve. So this is what we did here. So one is alpha 2x, one is 4x. So how to go from 2x to 4x times 2? Okay, so this x here, is referring to the O variable. Okay, it's the O variable here. Okay, so it's not this s, it's purposely put as x. So it's the O variable here. How about here? How to go from this 2 times 2x minus 1 to 4x minus 1? Can you try and figure out? And how to go from 4x minus 2 to 4x minus 1? Huh? Okay, here I wrote that it's x minus 1/4. Okay, so if you change the x to x minus 4, then it works. X minus 1/4. Okay. Okay. So you just substitute it in. Okay, you just substitute it in. And then how about the other one? So what you have to change to s so that you get 2s minus 1. So how to go from 4s minus 3 to 2s minus 1? Wait, let me see. Do I get the wrong parameterization? Check. Yeah. Okay, here I wrote 2x minus 1. Let's check, is it correct or not? Okay, so let me write out this. This is 4x minus 2. Okay, let's check if this is correct. So if I put half here, then I get 2 minus 2 is 0. Okay, good. 3/4, put here, 3 minus 2 is 1. Okay, this is good. Okay, so from where to where? Hey, I think I do the other way around, right? So in my note, I do this way. So I take a half. So it's going from here to here. Okay, I take half x. And then going from here to here, then what am I doing here? So here to here, I divide by half. Here to here, then isn't it I just minus 1? Man? I think it's just minus 1. Okay. And then how about the other one? 2x minus 1 become 4x minus 3. So you time 2. So you get 4x minus 2 and then minus 1. Okay, you get 4x minus 3. Okay, makes sense? Okay. Okay. And then what you need to prove here is actually a lemma. A lemma that is so if a path delta, okay, is obtained from another path gamma by reparametrization, then alpha and gamma is actually homotopic. Okay, so you need to produce this homotopy here. Okay, what's this homotopy? What's this homotopy here? Maybe I don't check it on the spot. Maybe you can discuss. If you have, what do you have? So let's say let gamma be half. Okay, be half, and then and also phi, okay, as some continuous map. Okay, such that it fixes the starting point and the end point and can do whatever in between. Okay, this is what reparametrization is. Okay, you substitute a continuous map into it, but fixing the two endpoint. Then we can give a homotopy between gamma and gamma composed with phi. Okay. Okay, so you should imagine that this, you see, this 2t here is a continuous function I put in. Okay, so your alpha t become alpha 2t. Alpha 2t is a continuous function. You do 2t first, only you do gamma alpha. Okay, so What's the homotopy between these two? It's not hard to write it down. So it's a map from the product of interval ST to gamma of Tx plus 1 minus T alpha x. Okay, let's see what is this homotopy doing here. Okay, so we put the linear homotopy inside the variable part this time. Okay, so you see at time 0, what happened? It is just the usual gamma x, the usual gamma. But if you put time 1, what do you get? Wait, did I do it opposite way? I think I do it the opposite way. So if you put 0 in, what do you get? You get the reparametrized gamma, phi x. Okay, this is the delta. And then if you put time 1, you get back your gamma x. Okay, and then how to constitute a homotopy? So this family should be continuous. Make sense? Okay, so this is a bit different. Instead of changing the endpoint thing, this is changing the variable. Okay, let the variable varies. Okay, any question? Okay, you should check this homotopy works. And then, okay, before we take a break, right? So there are 2 more things to check. Yeah, there are 2 more things to check. So there are 2 more things to check. Let's do it. So one is the identity. Okay, so let Ex naught be the constant part. Okay, Es naught be a constant part. So you need to argue to me that, oh, why if you compose with let's say alpha with Ex naught, okay, is equals to the path alpha is equals to the Ex naught composed with. So can you imagine what's the technicality happen here? Again, the speed up problem. The left hand side you speed up alpha, okay, first, and then you speed up Ex naught. But on the right hand side, you speed up Ex naught first. So there's again a reparametrization problem because one is 2x, one is 2x, and then the other thing is their order is different. Okay, because first you do alpha first, this one first you do constant first. Okay. And then this one is just alpha itself. The alpha is just alpha itself. So should we write down? So let's write down. So we need to check that Ex naught star alpha is really homotopic to alpha, and then homotopic to alpha star Ex naught. Okay. Yeah. Okay, this is the thing you need to check. Okay, so you need to produce this homotopy here. What's this homotopy? Okay, but really, what is these 2 things here actually? Okay, so these 2 things here, if you really write down the composition, okay, do Ex naught first and then do alpha. What you could really see is we could define Ex naught alpha as alpha composed with some phi I, and then the other one also alpha composed with some phi 2. So what is this phi 1, phi 2 here? So let me write down for you. So phi 1 is really doing a map, a continuous map on 0, 1, 0, 1. So you could imagine that this is a parametrization. Okay, so t goes to 0, 2t minus 1. And if t is in between 0 to half, and then the other one is half 2. Okay, so you see what happened to this phi 1 here. It tells you that if your time is in between 0 and half, what do? You send your time to 0. This is what the constant path do first, right? You stay there first. You stay there first. You stay there, and then the other half of the time you only move alpha. So the other time, from half to 1, you do the alpha. 2t minus 1. Okay. Similarly for phi 2. Okay. So phi 2, can you imagine what should I do? Should I move alpha first or should I stay still? For phi 2. I need to do alpha first. Okay, so if I do alpha first, what do we do first? We do 2x first. Okay, because we speed up already. And then for the half of the time, what do? We stay there. Okay, we stay at 1. Okay, correct or not stay at 1? Because if you put half into the speed up time, 1, right? And then for the other half of the time, we stay there. Okay, but since in this case, we write it as a parametrization form, right? We write it as a parametrization form. Just now we show that no matter how you parameterize, those two has a homotopy. And then this homotopy is produced by this. So you can see that the homotopy here actually depend on the phi 1, phi 2 you have here. Okay, make sense? Question? Got question? Yes, which part? Up, down, down. Oh, I think we should use let me think. What should we use? S where I think
Yes, just
reuse T. Reuse T. Should we change? Wait, let me think first. Wait, let me think. Okay, we input. Okay, wait. So this is a problem like, okay. So our alpha use S, right? Okay. So I think supposing, because we want to do reparametrization, so I think use S, S to S. Okay. So here all of this is S. Okay. Okay. So they are homotopy. Why? Because we proved the lemma already. If it's just differ by a reparametrization, then I produce you the homotopy looks like this. Okay, so you need to convince yourself why this homotopy will work. Okay, for different parameterization. Oh, lastly, what happened? And last a bit tricky, Okay, the last one is a little bit tricky. Okay, so should I show it to you? The last one is a bit tricky. Yeah. The last one is a bit tricky. The actual one is a bit confusing. I cannot say it is wrong, but I didn't write down the explicit form. So we just show one of them. We just show the other one. You can try it out. We'll just show alpha star alpha bar is homotopy to S. Okay. I think the homotopy I write down is what Hatcher trying to say. Okay, so consider this homotopy. I mind you a bit. Hatcher is a guy that didn't write down the explicit form, but it will explain it in words. So make sure you know how to translate into notation. Okay. So this is what it is. Okay. Instead of asking how I get these right, try and check why it works first. Try to check why it works first, and then try and think about how you can think about this thing. Okay. So similarly, we still have the two parts. Okay. Because of the speeding up, right? Then try check why is it work. Then let's to check this work, right? What do you need to check? You need to check endpoints, right? Okay, so let's check what happened at endpoints. So when t equals to 0, or you get gamma st, gamma s0, which is alpha 0. Okay, which is always s naught. Good. Okay, so one side is the constant path. The other side, this is the magic part. I think this part pretty much determine how you construct this homotopy. Okay, let's say you substitute t equals to 1. What will happen? You substitute, just substitution, right? Alpha 2x and then alpha 2 minus 2x. But what is alpha 2 minus 2x? This is a mystery. Actually, this is just alpha bar 2x minus 1. Still remember our definition of inverse map? Can anyone tell me what's the definition of inverse map? What's the definition? Let's write down the definition. Alpha of what? Okay, let's write down the definition here. Alpha bar t equals to what? Alpha t minus 1, is it? Alpha bar t equals to what? Is it t minus 1? 1 minus t, Okay, thank you. Yeah. 1 minus t correct now, because you put t equals 0, you get the endpoint of alpha. You put t equals to 1, you get the starting point. Okay, so if you apply this definition, right, include that alpha bar of 2x minus 1, you get what? 1 minus 2x minus, so minus 1 become plus 1. So exactly 2 minus 2x. Okay, so here is, by definition, it is the 1 minus 2x minus 1, this thing. Okay. Okay, so this should motivate how you build this homotopy here. Okay, any question? So you could imagine if you want to do the other direction, alpha bar alpha, what should you do? You just swap these two. Okay, swap these two and then do the appropriate reparametrization here. Okay, so how to get a reparametrization? You need to check with these two endpoints. Okay, the n path. I cannot say endpoint. The n path. Okay, the two n path swap. Okay, any question? Enough. We only check the starting path, ending path. We still need to check the endpoint of every path in the family. Okay, so how to check that? So that one is you let your v varies and then check the endpoint, the starting point and the endpoint of your x. So if you vary your t, so you check the family of path. So see where they start. Okay, see where they start. Start at 0 and also start at 1. Okay, but what are these? If you go and substitute it in, first is alpha 0. The other one is also alpha 0. Okay, if you substitute it in. But alpha 0 is the same point, which is S. Okay, so it's really a loop. For every time you put in, it's a loop. Okay, why is it continuous? Okay, note that you see, we define it piecewise. So if you want to show this kind of map is continuous, what should you do? You should check that both of them is continuous and then they they agree at the meeting point. Okay, so you need to use the testing lemma. Okay, testing lemma. So this is our general topology start useful. Okay. Wow, it's 308 now. Okay, so before we break, let me ask you a last question. So for a convex set X with a base point X naught, what is the fundamental group of a convex set? Trivial group Y. Yesterday we proved that what in a convex set, all paths are homotopic. In particular, they are homotopic to the constant path. So it's the identity path. So there's only identity there. All loops, yeah. Not just path, but also loops. Okay, loops. Okay. Any question? Okay, so first example you learned was if X is a convex set in Rn, then pi 1 of x naught for some base point is just the trivial path, which is actually generated by the constant path of S naught. Okay, I think this is not precise yet because we're actually considering the equivalent class. Okay, make sense? Everything is homotopic to constant. All right, any question? No? Okay, everyone got the different link yet? If not, you can go around during the break and then play around. Okay. Different notes and link. Okay, so let's break until 3:20.
很奇怪，
怎样？我只是造一个 parameterization 罢了，我没有给你 homotopy。
这里有。
对，
其实
我这个是在算他们的 composite， 他们 representative 的 composite。
就从这里你就讲看它的顺序是什么？
什么叫顺序？
就是这个先，
对，没有错，对，没有错，
这个先在这边。
对，没有错，对，没有错。OK，你是说我讲算到这些东西哈？
就你从这里就看得到它的顺序。
看得到，我的时间有跟呢，我的时间，
我就是跟死人组。
对对对对，只是说这个东西你要从这边开始算，我再放这个。
S 也是时间，T 也是时间，
哪里有 t？ 这边没有 t，
这没有 T 了，
这边没有 t。
所以 S 也是时间。
看你在讲哪一个时间，因为 homotopy 的时候就有两个时间了。如果你把 那个 path 也看，一个是走的时间，一个是变的时间。你可以这样子。对，
也就是走 alpha，走 beta，走 gamma。
对，
就我就知道它这个乘起来的。
对你这个两个乘起来呢，so 你这边是 2x 嘛，那这个就是 2x 减1，对不对？然后你在这整个要乘2，然后这个就变成 2x 减1了。所以你这边要 adjust 2倍。这时间会告诉你怎样去，对吧？因为你看这整个的话，一半在这边嘛，对不对？然后这个又分一半嘛，这样1/4也不是在这边，对不对？然后这个也是这样，这是一半的。
因为我可以，其实有很多方法，
哪里办法？
所以我表一半也可以。
等你就是换我们的 definition 了，我觉得可以，你换我们的 definition，但是我们不是已经证明了吗？你 parameter 来 parameter 去也是一样的吧 ？standard 就一般了。
走什么线？我应该走北大和伽马线。
那个
这里
没有，你也是走 alpha 线，只是说谁先 speed alpha，对吗？全部都是走 alpha 线的，只是看谁在，因为我们呀，因为是 technicality 来的，其实就是我们 concatenate 的时候，我们需要 保持这个零，说会变有这样的情况，所以才会有顺序的问题。但是你走的方法是一样的，其实你走的路线是一样的，只是你一个跑比较快，一个跑比较慢，你懂吗？
所以就是因为你血量层的关系，它还是要赶alpha先。
对，它其实路线是一模一样，只是说这个跑快，跑慢，跑这个慢，这个是跑慢的，然后或者是跑。
但是我们不应该要看这里先，然后再
没有，我们就是从刚才就讲了，我们一直从 left 看到 right。
哦，所以
我们都是从 left 看到 right 的，整个 product 出来都是一样的东西吧。I mean 从 point 的角度来看是一样。
那很奇怪，就是讲我 left 到 right 看的话，
对，
我在存这一个我不知道已经有了的东西。
有，它有。你这个乘的时候，你可以把它当成 beta 跟 alpha 来看的。但是我们乘的意思是说，是这里加快线，但是走的东西是一样的，其实。你懂什么意思吗？
两边都加快，就是
嗯，
就是我先把这个
这后面才加快，这个是后半场我才加速，这个我前半场就加速了，明白吗？
对
走是一样的东西，只是说这个是前半场加速，这个是后半场加速。但是你遮住这个看，它是一个 valid 的东西啊，没问题。
这个讲真的，
我就觉得
你觉得怎样？
觉得什么？
你觉得什么？
那你可以直接不看这一个速度啊，直接把它当成一个 part 来思考的。
就我就是觉得很 associative 很废啊，在这里。
associative 啊，
如果也是一直走到右这样的话就很废啊。对啊，我就
重点是你看这些 parameterization 不一样，那我们就不可以直接讲它们是一样的东西嘛。
这样的
function 要一样的话是，
我们 define 是 define 在这一个，我们 define 是 define 在这个 path 的这个 function 上面，这个 mapping 上面。
对，因为你看啊，这边的时间到1/2都是用它嘛，但是你这个时间放在这边是跑 beta 哦，他们会不一样的点，知道吗？所以我们不能够 as function 是一样的东西。
他们的 map 是
虽然那个时间我们不一样，但是我们会有一个 homotopy 慢慢把它变成一样，明白吗？你懂什么意思？确实我们跑的东西是一样的，我迟早会到你这个 beta， 但是怎么到呢？这个 homotopy 告诉你，可以这样讲吗？啊？
直观上来讲，路一样就是一样，但是我们从
在这个
定义，但是我们从定义上，我们定义 path 来讲，我们就用一个 map 和一个 time 来定义一个 path，这样就会导致路一样、速度不一样的东西会变成不一样的function，不一样的。
对，它在function上面讲就是不一样。
我们再用 homotopy，再把同样不一样的速度变回一样的 path。
我觉得你可以这样讲，我觉得你可以这样讲，我觉得这个结论是对的，我觉得结论是对的。对，那你可以这样讲，对。路是一样，
真在这里的话是 alpha 跑最快的哦。
不对吧？
在
这里最快，
对，后面最快，因为
后面先走。
我们的乘的定义是时间分对半，
对，
所以这个两个是1/4、1/4、
所以严格来讲，我们其实是做这个先的。严格来讲，
不
只是因定义的关系，然后我们拿这个乘的时候哦，这个又变了。
我们的
OK
上每一个乘，
当你讲做的时候啊 ，for 我们那看 path 我们是走 path， 但是你的做是真的是这个做。你懂我什么意思吗？我们在讲做的时候啊，我们通常想的是 path 在走，但是你的做就是 concatenate 的做，确实是 concatenate 先。但是问题是我们看这3个东西的时候，我们还是把它当成 path 来看。你懂什么意思吗？
因为它是一条啦。
对。通常我们讲做的话，我们是把它看成 as a whole path 是一样的 path， 但是
其他就是一样。
我想一下会不会一样哈？OK， 不太一样，其实我们不太准确，因为还有 equivalent class 关系那一层。
就是
那一层的，
还有一个分
还有那一层，因为这一个我们是已经 pick representative，对啊，其实这一层好像少讨论了 equivalent class，但是就你可以 compose 那个 equivalent class homotopy with 这个 parameterization homotopy。
它的 equivalent class 怎么都好，你把它想成三阶，它就是会扭动的，
你懂我什么意思吗？
知道吗？
你懂我什么意思吗？
对对对，
它是会扭动的三阶的，
你也可以讲会扭动，但是你看这边其实还有一层要讨论的，你还要讨论另外一层这个东西，但是这一个可以 compose with 这一个的 homotopy。
就其实他们全部 representative 海面上面都想了嘛，那个层。
对啊，对，如果你把你那个 well defined 那些讨论进来的话，那你就要 compose 这两个的。呀，对，那个过了过后，我们就可以随便选 representative。
这个里面你要讨论到很乱，三层哦。
然后我觉得也有必要了，因为
有必要的，
我觉得有必要，因为我们定义是从
如果单看这个有必要啦，但是如果我们已经把它当成一个 lemma proof 掉了，就没有必要了。对哦，单看这个当然有必要了，但是如果把它当成一个 lemma proof 掉就没有必要，因为 by induction 嘛。
Yeah，
我们 proof 会 proof 两个了，就 proof 三个。OK，
就觉得很
有什么？废，废但是好玩，它会出很好玩的东西。OK， let's start. Okay, so right. So if you look at this composition, right, this associative composition, really, if you are a path or an n moving alpha, beta, gamma, both of them are the same path. You move the same, distance. But the problem here is the way you run. For the first part, you sprint first. Alpha, beta, you sprint. And then you move gamma. But the second part, you walk alpha first, and then only you sprint beta, gamma. So this is a difference. So they are differ by function, as a function, they are different. You see, here, the time is half, you can use alpha. But then, here times half, you have to use beta. They could potentially be different points. But the point here is there is a continuous map that connects these two. This continuous map is a higher dimension. It's not line anymore. It's a family of line. Okay, understand? Okay, so for example, how to use this thing? You look at this table here. So if you look at this boundary, okay, this boundary here, right? Okay, homotopy is like the thing that covers this table. So you can use homotopy to build object. You can use homotopy to build object. Okay, so you can use homotopy to build the things in between. This is the usefulness of this homotopy. Okay, later you will see this very precise actually. Yeah. Reparameterization is just a different speed. Different car, yeah. Okay, different car, sure. Yeah, different car. So it's one of them maybe is rocket, the other one is a lorry, for example. 车然后OK， 还有 overheat 这层关系 OK 来 yeah of path you try 不一定，其实不一定，只是说 Rn 会找到它我们现在讨论 we only discuss convex set in the Rn. It's not true that every topological space will have this kind of space, convex set. Okay, so the convex set here is to allow linear homotopy to exist. Okay, maybe in some other cases, linear homotopy doesn't exist, but still, the fundamental group is still identity. Because you can put another homotopy as long as all paths is homotopic to the constant path, then the fundamental group of X is the triple group. And then we will say that this space is actually contractible. Okay, this X space is contractible. Contract, right? Contract to one point. Okay, you can contract to one point. And then how to contract the space? Through this homotopy, right? If you trace through this homotopy, then you know how to go to that point. Okay, I think we need to speed up a little bit. Okay. So next proposition. Let's say, let's not write a lot of words. Let's draw it because the word already I put inside the notes. You can look at it. So this space is X. Let's say this is the alpha path. Right. So we claim that there is a induced map from alpha, called alpha star, from high one of xx1 to high one of xx0. Okay, so what does this mean here? Domain. What's the domain here? The domain here, so my alpha, I need to orient it. So the starting is S0, ending is x1. And then pi 1 x1 is what? A loops around x1 like this. Okay. Pi 1 x0 loops around x0. Okay. So what do you think? It says that, oh, if I give you a loop at x1, it becomes a loop in x0 using alpha. Can you try and construct this? I already tell you how to connect. Can you piece them together? So you need to produce a loop that based in x0. So I give you a loop at x1. Okay, maybe I give you a loop here. So how to make it a loop that starts from x0? Any idea? Any idea? Where? So I mean, loop start at x0. You should start from x0 first, right? And then somehow you need to connect to your gamma. Can connect? Can connect or not? Your gamma where's to start? x1, right? I tell you there's a where from x0 to s1, right? So what you should do first? You walk alpha first, and then you go through gamma. Is it a loop at x0 yet? You have to go back. You have to go back. Then it becomes a loop at x0. Make sense? Okay. So what's the composite here? You do alpha first, and then you do gamma, and then you do alpha inverse. What is this? What is this here? From AA. Can you recall now? What is this? Multiply by alpha and then at the back inverse. What is it? What is it? What is it? What is it, Adrian? What is it? What's this? Not quite. Later we will meet normal subgroup, but what's this thing? Multiply by alpha and then alpha inverse. Conjugate. Okay. So this alpha path here will induce a conjugate map. Okay, conjugation here. And then moreover, you see, we are talking about map between groups, right? We want it to be a homomorphism. But more than that, this is actually an isomorphism. So meaning it is invertible. Okay. Can you imagine why is it invertible? What is the inverse? What do you think? Work backward. So you take the A inverse and then induce it. So if you work backward, what is the okay, now we just straight away tell you what's the inverse of this A star here. So basically you send gamma to alpha bar first, and then gamma, and then alpha. Okay. Yeah. And then this space obviously go from pi1 of xx0 to pi1 of xx1. Okay, no? Okay, so this one I left you to check it. This one should be easier. Very similar to AA argument. The hard thing we already done it just now because the well-defined thing, how to take product, all those things we already set in the group. Okay. Actually, there's a categorical property happening here. Okay, I'll make it a remark here. Later we'll talk more about categorical observation. But now let's write down the very primitive observation here. Let's say if beta is a path that go from x1 to x2, okay, then you can compose them. So you can look at the concatenation of alpha beta because it's another path, right? Okay, so what's this induced map is? This induced map is actually alpha star with beta star. Okay, so and then this map is going from pi1 of x2 to pi1 of xx0. Okay. Okay. And moreover, if pi1 xx0 is abelian, okay, what do you think if it's abelian? You can commute path. Okay, if you commute path, what happened? Then for any two path, alpha, beta, from x to x1, okay, we can check that actually they induce the same map. Okay, actually they induce the same map. Why? Because you could imagine that. Let me write down. So you could check that this is like alpha composed with beta composed with. Okay, if it is commutative, then the alpha and alpha star will cancel out because it's commutative. Okay, so you just left with like that. Okay. So anyone recall that this is a very similar structure that we have seen in algebraic geometry? If you still remember the polynomial map, pullback. Yes, if you compose two pullback, okay, then you will get this kind of structure. Yeah, so in that case, it's contravariant. For this case, it's covariant. So following the sequence. Okay. So these are simple check. You should check it. So let's put the corollary here. Let x. Okay, so no need topology space. We always in a topology space. So if x is path connected, okay. So path connected means what? Every 2 points there exists a path. So for every 2 points, you can do this alpha thing. Okay. So what's the implication here? The group pi1 x0 is actually the same no matter where you put the base point because there are isomorphism between all the base points. Okay. So up to isomorphism, it is actually independent of choices of base point. Okay, because every loop in X is conjugate to another loop, okay, with different base points. Okay, from what we have seen just now. So in this case, base point become not important. Okay? Become not important for a connected space. So for connected space, path connected in particular, need the path. We need the path to work. not just connected. So we need the path. So we will just write pi 1 of x, or sometimes you see pi 1x. Okay, it's just pick any base point and then consider the loop space around it. So for example, Rn is path connected. No matter I choose the origin or choose 1, choose 2, choose 3, it's the same pi 1. Okay, we don't care about base point anymore. Okay, base point can disappear. But obviously, when we talk about a loops, for sure we need to fix base point. But the Topology tells you that I don't care where you pick your base point. It's the same pattern you will get. Okay, for that space. Okay, understand? Understood? Okay, for path connected space, base point doesn't matter. Pick anything you like. Okay, so next definition. I'm not sure you come across this or not. I think we talked about it during calculus 2 at least. A topological space is simply connected. Okay, so now we have a precise definition here. If it is path connected for sure, and has a fundamental group. Okay, so what does this mean? So just now I show you that everything should be able to contractible to a constant point. Okay, and has a trivial fundamental group. Okay, you could imagine something is path connected but not trivial. Can, right? Can you imagine that? What is the thing? Donut, a square, S1, okay, path connected but not trivial, right? Okay, every 2 point you can connect, okay, but you cannot shrink. Okay, so this is S1. Sometimes it is this, sometimes it's S1, so you need to be careful. Nothing inside. But does there exist? Okay, let me test you a bit. So I said that every loop is not contractible to a point, right? But any contractible path or not? Any contractible path connects them. So path that can be contracted to a point. Loops cannot, but path length can, right? So I just pick an arc, right? I just pick an arc here, portion of it, and then my homotopy is like, okay, contract to a point. Okay, and maybe an exercise if you want, write down the homotopy. Yeah, please. This exercise you have to do. If you say I don't understand, I don't understand. You don't do, then how you understand? Okay, you have to do this exercise so that you understand. So please write it down. Because I cannot write everything in this class. Okay. Next proposition. So a topological space X is simply connected if and only if there exists a unique homotopy class of path connecting any 2 points on index. Okay, let's think about this proposition first. What is it trying to do? Okay, so just now we said that it's simply connected if it is path connected and also have a trivial fundamental group. It turns out that the trivial fundamental group get translated to the homotopy class of path that connecting any 2 points in X. Okay, very convenient. So it says that what does this mean? Up to homotopy, there's really only one path you can draw between 2 points. Correct or not? Yes. Okay, up to homotopy, there's really only one way you can draw. Okay, so for example, because R2, let's say R2 is simply connected, right? So up to homotopy, there's really one path between 2 points, correct or not? Every path is homotopic to this straight line path, for example, in R2. All right. So if you want to go, 我要去撞一下南墙再回来。 it's still homotopic. Okay. Okay 呢？我去北极玩一圈，去南极玩一圈再回来。Okay, still homotopic. Okay. Okay. So yeah, so why is it true? I think one direction is easy. Which direction is easy? What do you think? Which direction is easy? Which direction is easier? So one, you assume pi1 trivial and then prove that there's one unique homotopy class connecting 2 points. One is assume there's a unique homotopy class connecting 2 points and then prove that pi1 is trivial. Pi1 is trivial means what? Every loops, right, is homotopic to the constant loop. But loops is a path that connect 2 points, which is the same point. So it says that there's only unique one. No? There's always one path that connect the same point. What's that path? Trivial path, constant path. But unique one only can be trivial. So meaning from the right to left is easy. It's a specialized statement. But how about assuming you know what happens to loop? How do you talk about path between random 2 points? Okay. First of all, we are simply connected, right? So we are path connected. So meaning that at least there's a path already. But now we want to show that it is unique. Okay, how to show it's unique? Yes, same trick from your FL algebra. Okay, same trick from your FL algebra. So let's do it very quick. So this direction is easy. And then the other direction, okay, so path connectedness would imply existence. Again, now we want to show uniqueness. So suppose pi1x is 0, okay? And suppose gamma and delta are two paths from x0 to x1. Okay, so how to show that alpha and gamma is the same? We don't want it to be exactly the same, as long as they stay in the same homotopy class. So meaning you need to produce a homotopy between these two. Given that you know about loops, how do you know about path? I would say that this is very related to the inverse thingy you learned in extra algebra. Inverse. How to prove inverse is unique. How to prove inverse is unique? Because I tell you the identity, right? As long as you get the loop, you get the identity already. You produce loop or not? I tell you two paths, right? So draw it. You need to imagine it, x0 to x1, right? So you got a gamma here, and then you also get the delta here. Got loop or not? There's loop here. Okay, so you can write down that then gamma is homotopic to gamma composed with a loop, which is what loop is useful here? Delta bar and delta. Is it a loop? Okay, and then can we contract one of the loop or not? Is there another loop here? So is delta gamma bar another loop? Yes, right. You go gamma, you go delta bar. Okay. So okay, I think if precise, maybe follow what Lydia said just now. So let's do this one, EX. E at where? E at x1. x1, okay, good. And then we contract it to ex2, right? And then with delta, and then this is just delta. Okay, makes sense? Makes sense, huh? Okay. So one is the loop at x1, the other we view it as a loop at x2. Okay, so these two are homotopy. Okay, any question? Question? Got question? Okay, it's a very nice application of abstract algebra. Huh? Okay, in that case, let's touch a little bit on the fundamental group of x1. Actually, we will spend a bit of time here. So let's talk about pi 1 of x1. Because x1 is half connected, right? I don't really care about the base point. But when we really discussing the loop, we need to fix the base point. So first lemma I want you to keep in your mind, which is very useful, is we're gonna chop things out. So we need this lemma here. You still remember the Lebesgue number lemma? Anyone can recall not? What's that thing doing? Something finite ball. Yeah, cool. Okay, good, very good. So, okay, maybe I can bring out the exact thingy. So, try and remember this facts here, because we're going to use a result from this Lebesgue number here. So, this is the picture, I guess. Okay, so if you have an open covering of your compact set, then you can always find, okay, a subset B that is small enough, that has diameter less than delta, such that there exists an element inside your open cover, and then this B will stay inside it. Okay, all these B have to stay inside some open set in your open cover. Okay, okay, can remember this diagram here? All right, so I think we're not gonna prove this, but this result is gonna be used later. Where is my note? Here. Okay. So this is the result of this Lebesgue number lemma here. So let's say if you have a map from a product of unit number into a topological X. So the compactness we're going to apply here actually is the compactness of the closed cube. So cube is compact, you still remember. And then let X be open cover of X. Then there exists an n in n such that what? Such that this n we're gonna chop out our unit cube here. Okay. We're gonna chop the unit cube by n, and then this product here, again the image of this product here will live inside one of the open set of open cover X. Okay, so we are applying the Lebesgue number lemma on this compact set here, closed cube. Okay, I use the compactness to chop up my unit cube. Okay, actually this one is a bit tricky here, huh? This one a bit tricky here. I can pick any one of, you know. This is small n and this is not big N. As long as you pick number from 0 to -1, every small pieces will lie inside. Yeah. Make sense? Okay. I think we're not gonna prove this. Sorry. I include the proof inside the notes. We're not gonna prove this. This is like a general topology proof. I think not too hard, not too long also. Okay, if you want, you can have a look. 什么？麻烦？会麻烦吗 actually? Actually, not really 麻烦 not really 麻烦, but you need to understand what happened here. Okay, so the picture is here lah. If you want to have a look, I borrow from. Yeah, this note is coming from the 5,000 pages national. And then note is actually very detailed. Okay, if you want to have a look. Okay, yeah, if you cannot understand Hexer, you go into this one. Yeah, so there's a F, right? Mapping a unit cube into some X here. And then you have some open cover VI of your X. Okay, so the claim is you can chop this unit cube enough so that the cube will stay inside the VI. Okay, so the cube will stay inside the. Okay, for all the VI or for some VI, let me see. Oh, there exists some VI that it could stay inside. Okay, yeah, can see or not? Can see the grid. Where is his VI? Huh? What's his VI? Let me see. Oh, his VI is the purple one, and then the red one. What is the red? I need to check back what he's doing. Huh? No red. Is it true that how many VI he got? This one, 1, 2, 3, 4, 5, 6, like that. I think I need to check what's this VI. I go back and label properly. If not, I draw my version. So you want to make sure that this grid will lie inside one of the VI. Make sense? Okay. Yeah. Okay. Later we will use this result. And then we introduce what is lift. What time is it now? Okay, let's finish at lift. So we introduce lift. So lift, we introduce a lift of a map into X1. Okay, as long as you are continuous map into X1, okay, from any topological space, we define this lift here. So what's this lift of this map? So look at this triangle. Okay, so in this course, useful friend, a handy tool is commutative diagram. And this is the commutative triangle. Okay, so if you have a map from W to X1, I got a lift. Okay, lift to where? Lift to a map from R to W, from W to R. Okay. But this lift, what is the special thing about this lift here? Is we always have a map from R to X1 like this. This is your calculus 1 thing. So 2, calculus 2. Okay, T to the E to the IT, then you will go into the loop. Okay, so if we parameterize this X1 on, I think you need complex number to draw this, right? So on the complex scale. Okay, sometimes the book don't use complex number, they just use R2 is similar. Okay, then you will use different description. But the end goal is, after you compose this lift with this projection here, it is the same as that. And this happened in your real life, you go exercise, you go to the field and track, how you run? You run in a circle, right? But your clock measure how far you run, which is real number. Okay or not? Your partners look around your X1, look around your track and field. Understand? Okay. How about we stop at here? PT. P meaning you run how many rounds? Instead of telling people, hey, I run 50 km or I run five rounds of the. Could be. Or you tell people yeah. Some people will tell you, oh, I run. One full round is how many meters? I forgot now. How many meters? 400, Okay. For example, in your X, you run 800, right? Then after P, you will tell people, oh, I run 2 rounds. Like that. Understand? Okay, so after P, the unit become circle already. It's not meter anymore. Okay, next sense. Okay, so this is the idea of it. I think we should chow. Okay, we'll start with lift next week. So next week we will have pop quiz. please be ready. Do exercise. Okay. See you next week.
Ah，一个 blow up 这样。